Okay, a couple terms I am going to hold you to, though. And that's the idea of a spring tide or a neap tide. If I line up the sun and the earth and the moon, and they're all lined up in the same plane, I can look at the tide on earth, and I can look at a component that's caused by the gravitational attraction between earth and the sun, and I can figure out a component that's caused by the gravitational attraction between earth and the moon. And in this case, the gravitational attraction of the moon and the sun all line up. So the bulge of water, the high tide that we're going to see, is going to be a high tide because the combination of the lunar tide and the solar tide are going to fall right on top of each other. They're additive. So in this case, it's what we call a spring tide. The high tides are going to be really high, the low tides are going to be really low. So as Earth rotates under this bulge of water, here's high tide, here's low tide. So you can see why these are the biggest waves on Earth, because I have two high tide crests, the bulges. I have two low tide troughs, these areas between the bulges. So essentially, I've got a trough, a crest, a trough, a crest. I have two waves that make up the entire circumference of Earth. So the wavelength of one of these waves is half the circumference of Earth. That's pretty huge. Now, that's going to happen when everything's lined up. New moon, full moon. Notice that's the beginning and the end of the month.
Wouldn't the full moon be weaker than the new moon? Because the moon's tide is pulling away from the direction the sun's tide. Do you see what I'm saying? Or
You're saying
am I just confused?
this should be bigger than this?
Yeah.
Yeah. A little bit, but not noticeable.
But why wouldn't it be more? Why wouldn't it be more noticeable? Because the moon's influence is so much more significant than the sun's.
Well, it's going to be more significant, but it's going to be more significant there. It's going to be more significant here.
Right.
Okay, so it does add in. The solar part is fairly small. It's this darker blue part. And you'll notice they've got this drawn, that the lunar tide, the whiter part, is the larger of the two components of the overall tide. Okay? Now, hold that thought. We're going to do a couple more things here. Okay. And if I don't answer you, come and catch me at the end. Okay, so that's springtide. Notice springtide does not mean spring, does not mean the season. Okay, this is happening every new moon, every full moon. Now, what happens when it's first quarter or third quarter? And again, I've got moon lining up, and notice the big bulge of the lunar influence? And here's the solar influence, a much smaller influence, but notice they don't line up now. The moon and the sun are right angles to each other. So now the lunar tide kind of fills in the trough. The solar tide is still there, but it's smaller. So I don't see a big difference between the tide levels. The range isn't very big anymore. It's not additive in this case, it's subtractive. So at first and third quarter moons, we have what we call a neap tide, and that's where we see the tide not really change a whole lot, not a big range at all. It kind of cancels itself out.
Is there any real effect from having that first quarter of the neap pulling the way it is with the solar tide pulling out the way it is in that overlap area?
Yeah.
'Cause it looks like it's pulling away from each other.
Sure. They're overlapping, and that's going to continually change as the moon and the sun change their angle. So as this rotates around, you're going to see this bulge get bigger as it moves to complement the solar tide at full moon. So this is kind of an ongoing process. Okay, it's transitional.
So it's not pulled from the same spot.
No.
obviously, to the
No.
same.
No. Okay? So these are kind of the extreme positions. Okay. Now remember, the gravitational attraction is between the moon and the Earth. So it's not lined up along the equator. It's lined up directly to wherever the moon is in the sky. Okay? So let's do this. We're looking at Earth, and notice I've got the pole straight up and down. It's really angled a little bit, but just to make it simple. Earth is turning eastward, okay? And here I am. There's the North Pole. I've got this little island. It's at the 45-degree parallel. And notice the bulge here is directly toward the moon. Okay? It's really handy if this thing works. So, the bulge does not line up with the equator. It's really kind of pointing up toward the moon at about the 45. So as I rotate this island around Earth during its 24-day or 24-hour rotation, you'll notice when it's off to the right there, it's directly under the bulge. So we have a maximum high tide. It comes around, it's on the back side of the planet, it's at low tide. It comes around to the next high tide there on the left, but notice that the next high tide is not directly under the center of the bulge. It's off on the edge of the bulge. But the bulge is aligned to the moon, not to the equator. So my second high tide of the day is a much lower high tide. So what I'm seeing here is I'm getting 2 highs and 2 lows for a tide every day, but they are distinctly different heights. And this is going to change depending on the relationship of the moon and the Earth, and that's going to be a seasonal issue. So we have a couple terms to know. What we see is if we have 2 highs and 2 low tides every day, we call that a semi-diurnal tide. Diurnal for day, semi, we're getting 2 tides a day. Cape Cod, Massachusetts is typical of this. So every 12-hour period, you've got a high and a low. Now, other things get in the way. Things like continents, enclosed bays. The water simply can't move around fast enough, and it can't keep up with the tidal forces. So in some areas, I only get 1 tide, 1 high, 1 low a day. I don't get 2, I just get 1. Mobile, Alabama would be typical of that in the Gulf of Mexico. The water just can't move in and out of the Gulf fast enough to have 2 tides a day. We call that a diurnal tide. And some places I get a semi-diurnal tide, 2 tides a day, highs and lows. But like the example we just showed, we have 2 highs at different heights and 2 lows at different heights. And that is typical of the west coast of the United States, for instance, Los Angeles. And we call that a mixed tide. So some basic terms, and if you ever drag out a chart when you're out boating, these are the kinds of terms they'll use on the chart if it's an area that's subjected to a tide. Tidal range, height of the water at low tide versus the height of the water at high tide, that range can be pretty significant. In a lot of places, it's just a few feet. But in places like, well, here's the Bay of Fundy up in Nova Scotia. And here the tidal range can be anywhere from 30 to 50 feet between low tide and high tide. These boats sitting at the fishing pier, here it is at low tide. And look at the difference. So you think, well, that's kind of cool, but who cares? Well, you do if you're a fisherman in the Bay of Fundy. You need to know when you can get your boat away from the pier and out into the fishing waters. You need to know when your boat's full of fish, when you can or cannot get back into shore to offload. Nothing worse than having a boat full of fish and no ice. And look at the pier that they have to build because of the tidal range. You can see the truck on the pier here. So they've got to build it stronger, sturdier, bigger piles. Look at the cost of the facility they've got to put in. And you've got times when your boat's sitting in the mud, so, you know, it's getting beat up. So it adds to the expense, it adds to the complexity of the schedule. All sorts of things go on when you have to worry about it. And I mean, you can see the horizon in the top picture here. Look at the horizon in the bottom picture. This bay just totally empties. This is not just a little area. This is a whole big area. Okay. Let's shift gears and talk a little more about atmospheric circulation. Kind of ocean circulation, atmospheric circulation, they kind of go hand in hand. It's chicken or egg. You don't know which goes first. They're all kind of affecting each other. Basically, the atmosphere is pretty homogeneous. This lower part is just a mixture of gases, and surprisingly, it's pretty dry. Only about 4% of it is water vapor. So it's not this soggy, wet mass that you might think of, especially on a day like today. And again, density is going to play a big role in how this operates. And that's going to mean temperature is going to play a role. And certainly water content is going to play a role if we're going to change density in the atmosphere. And, you know, there's some little aerosols up there, particles of dust, particles that come out of spray cans, things like that. So that's all part of that atmosphere. But if you look at this picture, you'll notice, big hurricane here, but look at this thin little blue line here that just kind of skirts the edge of the planet. That's the thickness of our atmosphere. That's it. All this black is outer space. The gases that make up our atmosphere are just that thin blue line that you're looking at on edge there. A couple of terms that you hear all the time, and you probably all use them pretty interchangeably, but they're not, and that's weather and climate. Weather is short duration climate change. It's measured day to day. You know, you get the 8-day weather forecast. That's weather. And it's constantly changing. Climate, on the other hand, is a long period. Normally they consider it greater than 30 years. So our climate here is defined as a generalized trend. It's a long-term trend, and it's a composite of weather. I mean, it obviously includes summer, winter, fall, spring weather, and we look at it. And if you think about it, we kind of seem to go through about a 20-25-year cycle of really bad winters, and then they aren't so bad, and then they start getting bad again. And every 25 years or so, we kind of go through this up and down cycle. And that's climate, that cycle. If I look at what the atmosphere is composed of, it's pretty simple. It's essentially 79% nitrogen. Nitrogen's kind of just a filler. It's the stuff that makes you talk like Donald Duck, you know, when you inhale it. And 21% of it's oxygen. That doesn't leave a whole lot left for everything else. It basically leaves just a little under 1%. And of that, a third is carbon dioxide, and a third is argon. Argon. Why do we have, in a relative sense, why do we have so much argon up there? Very non-reactive, stable gas. And if you look at argon, it just doesn't do anything. It just sits there. It doesn't react. That outer shell's full of electrons, right? So it's stable. So argon just accumulates. It doesn't escape to the atmosphere because it's heavy enough that it has a escape velocity where it just doesn't quite make it. It pretty much just gets into the atmosphere slowly because it isn't very reactive. And once it's there, it just hangs out. So the fact that we know the reaction rates for argon and how much is in the atmosphere kind of tells us how long that atmosphere has to be accumulating to have the atmosphere composition it does today. Argon's kind of a key to telling us that. And it basically says we're looking at an atmosphere that's got to be millions of years old. There you go. Yeah. That's how we can kind of get a handle on the age of our atmosphere. Okay. Now you'll also know that 1/3% approximately is carbon dioxide. And we all hear about greenhouse gases and how carbon dioxide is the big culprit for global warming. And you ought to be asking yourself right now, I don't get it. How come? It's less than 1/3%. Our whole atmosphere is nitrogen and oxygen essentially. Why are we having this big greenhouse gas effect from carbon dioxide? I mean, it's barely there to begin with. We need a little greenhouse effect. You need to have a little to keep warm enough to have the climate that we have, right? So you need a little CO2 out there, and we've got a pretty fair amount. The big problem is it's such a small amount and it's so effective that you add just a little bit more. It's still under 1%, but it has a big effect. So for the amount of CO2 we have up there, it has way more effect than you think it would. So small changes of CO2 make a big change in the composition of the atmosphere and the way it behaves. The part of the atmosphere that we live in is this little bit right down here, right along the surface of Earth, and that's called the troposphere. And as you know, you start climbing up a mountain and it starts getting colder, doesn't it? What's happening is you're getting away from the heat source, which is Earth, because incoming light from the sun is bouncing back off of Earth as infrared energy. IR, or infrared energy, warms you up. It's heat energy. So as you start climbing up away from the surface of Earth, you're getting away from that source of radiant heat, and it's getting colder. Temperature is going to decrease. But then something really weird happens. You get into the layer of the atmosphere above the troposphere, which is called the stratosphere, and it starts to get warmer again. Well, that's kind of weird. Is it because we're getting closer to the sun? No, not at all. If anything, it's going to start getting a whole lot colder before we're done. What's happening is this is a zone where we're getting ozone accumulating. And as light from the sun, which is coming in as UV light, ultraviolet light, high energy shortwave light, it's hitting this ozone, splitting it apart, the ozone is very reactive, so it immediately recombines